Okay, now we switch back to our sister program, Innovation Crossroads. Next, take the stage is Shane McMahon, the CEO of Lux Semiconductor. Shane will speak about the intriguing developments in materials and methods to advance flexible electronics for IoT and other applications. Shane?
Yeah. Hi, everyone. My name is Shane McMahon, and I am co-founder and CEO of Lux Semiconductors. And we're developing next-generation thin-film electronics. So the single most important material in electronics is silicon. A thin slice of it, called the silicon wafer, is what every computer chip is built on. These computer chips are then attached to printed circuit boards that are used to power all modern electronics. There are over 100 billion circuit boards in use today, powering things like our phones and tablets, all modes of transportation, and even our household and kitchen appliances. But as the world transitions to smaller, lighter, and more embedded electronics, a new class of flexible circuit boards has emerged that relies on technology. Now, these flexible printed circuit boards are different in that not only can you print the metal like you can on rigid boards, but you can print the resistors, the capacitors, and other fundamental electronic components. Printing these components means that you can make highly customizable, low-cost devices. But there's still one major component that can't be printed, and that is the computer chip. So just like with standard rigid circuit boards, computer chips still need to be mounted and soldered into place. This creates manufacturing complexities, adds reliability and durability issues, and forces the flexible circuit to retain part of its rigid and bulky nature. Instead of attaching silicon computer chips on afterwards, what if we built a layer of silicon directly into the flexible circuit board and then patterned the computer chip into that silicon? This would mean no more surface-mounted components that are soldered in place and would actually lead to a fully integrated, completely thin film electronic solution. To do something like this, you need to be able to produce a sheet of flexible silicon, and that is exactly what Lux is doing. Leveraging a half-century of innovations in bulk crystal growth and applying them to low-cost thin films for the first time, we are creating an entirely new version of the silicon wafer to serve as a next-generation material platform for integrated electronics. Our silicon provides 80% of the performance of the silicon wafer, which is actually far sufficient for our target applications, at 20% the cost, all while being thin, flexible, durable, and lightweight. This silicon will enable Lux's core product offering, system-on-film electronics. Now that this flexible silicon is acting as the circuit board itself, it can support the patterning or printing of all electronic components. High-performance silicon electronics will be combined with low-cost printed electronics for the first time to deliver a truly thin-film electronic solution and ultimately create a new flexible circuit board to serve major emerging markets. Just one example is that in digital health. One major way to reduce costs and improve patient wellness is to actually measure physiological biomarkers using thin, flexible sensors and then sending that data wirelessly to a local hospital to be evaluated by medical staff for diabetes management, cardiovascular monitoring, and wound care, just to name a few. But as you can see, today's most advanced electronic solution requires the patient to wear bulky electronics on their arm. This same device, designed and developed on Lux's silicon, would convert the entire device into a thin film, making biosensors much more amenable to the human body. But there are a number of other major applications where converting to Lux's silicon would create new value. including the broader category of wearables for health and fitness, flexible and micro displays for augmented and virtual reality, ubiquitous and low-cost sensors for the Internet of Things, and the nodes to provide the processing and power to support them. Combined, these markets will be worth $340 billion by 2030, eclipsing in size the current semiconductor industry. But to truly enable these markets, the devices that serve them must have two of the three attributes: form factor, multifunctionality, and low cost. We believe that building these devices on Lux's silicon could deliver all three. To execute these developments, we rely on our team, which is comprised of myself and my partner, Graham Hauser, both PhD graduates from the College of Nanoscale Science and Engineering, and Louis Haber, a Cornell master's grad. To date, we've raised over $1 million in non-dilutive capital from major federal agencies, including the Department of Defense, the Department of Energy, and the National Science Foundation. And over the next 6 months, we'll be looking to raise our first seed round of about $1 million to begin scaling this technology. Thank you very much.
Shane.